Hello, guys. This is Ishan Akbar. In this video lecture, I am going to discuss the derivation of a differential equation for gradually varied flow. In the next video, I will try to solve a problem relevant to this GVF. This is basically a topic, an important topic from hydraulics engineering or simple hydraulics or open channel hydraulics. GVF is basically, as its name suggests that there may be a gradual change in what? A gradual change in water surface elevation or water surface with respect to length of a channel. What may be the cause of this change? There may be certain changes. That may be a change in slope, that may be change in the channel roughness, that may be change in the uh, river or canal construction, that may be due to a hump, that may be due to installation of a sluice gate. There may be any reason, there may be any change in the shape, that there may be any changes in the bed, that there may be any changes in the flow conditions, there may be any changes in the geometric conditions. So if the change along the length of a river or a canal is gradual with respect to the distance, that means we have a small change over a longer distance of the river reach or a canal reach, then that will be known as a gradual change or gradually varied flow. And that change may be due to slope, due to shape, due to roughness of the channel, due to geometric changes, induction of a hump, or due to installation of a sluice gate. In the figure below, you can see that there is a sudden change of water from this point to this point. We can say that level of water is decreased from this point to this point for a shorter distance. It increases first and then decreases suddenly. So this section is known as the RVF, mean there is a rapid change in the water surface elevation over a smaller distance. But here we can see that there is a small change in the depth or water surface elevation over a longer distance. Means there is a non-observable change, and if this remains constant, the water surface elevation remains constant with the depth, that is known as the uniform flow. And again, if the change is sudden with respect to distance or with respect to the length of this is the length of the channel, then again the flow will become rapid. So this section shows the gradually varied flow or GVF. So this is theoretically background, and now we will move towards the derivation of a general or a differential equation for the water surface elevation with respect to the distance. Here we are considering two sections, section 1 and 2, which are at a distance of dx from each other. The distance between section 1 and section 2 is dx, mean along the length of the channel, we have a length of dx, we have a distance of dx. Here we have a datum line. So from datum line, we will apply the energy equation at section 1 and at section 2. So at section 1, what will be the energy from datum line? What will be the total energy till this point? So basically, energy comes from, we can say that total head or total energy at section 1 is H1. It is comprised of three things: Z1 plus Y1, that is elevation head plus pressure head plus velocity head V1 square over 2G. This is at section 1. And again, if we go to the section 2, at section 2, the total energy H2 will be equal to Z2 plus Y2. Elevation head from the datum Z2 plus Y2, pressure head plus velocity head at this point, that is V2 square over 2G. And what is next plan, because we are moving from the datum line to a horizontal line to the total energy, you can say the total line. total summation line, because we are following the conservation of energy, it means that at point 1, at section 1 and at section 2, total energy must be constant. It means h1 and h2 must be same. So how these can, if we stop at this point, it means that h2 is not equal to h1. So how can they be equal? Because at point 1, from this point to this point, there will be a loss of energy due to frictional forces, or due to bends or any alteration in the channel. So those alterations or those fluctuations may induce a head loss. We can simply say that we will add head loss in the channel, HF, at section 2. So this is the energy line. The slope of the energy line is called as SE, and this is bed of the channel. So the slope of the bed is known as the S naught. This is positive slope, and this slope is also positive because the line is moving from left to right in downward direction. Moving from left to right in downward direction. Here the line is same, moving from left to right in downward direction. So this is a positive. This is S naught, slope of the bed, and this is SE, last slope of the first line near the datum, and slope of the last line near the horizontal line. So this is SE. This slope is known as SE. This slope is S naught. If we apply the Bernoulli's equation, it says that total energy at section 1 is equal to total energy at section 2. So we'll simply need to put the values of energy 1, Z1 plus Y1 plus V1 square over 2G is equal to Z2 plus Y2 plus V2 square over 2G plus HF. This distance between section 1 and section 2 is dx already, as written here, over here. So we can simply rearrange the equation. That is Z1. We can shift this Z here. This is Z1 minus Z2 is equal to Y2 minus Y1. Just keep elevation heads on the one side and other heads on the other side, plus V2 square over 2G minus V1 square over 2G plus HF, this one. So if we see at Z1 minus Z2, it means that this is the elevation head at section 1 and Z2 is the elevation head at section 2. So we can simply say that this depth or this distance is Z1 minus Z2. If we subtract this portion from this whole portion, if we subtract this portion, so what is this portion? This is Z2. So whole is Z1 minus this portion from this point to this point. So this will be Z1 minus Z2. We can say that this is delta Z equal to, from section 1 to section 2, there is a change in the parameters, or flow parameters, because Z is not a flow parameter. We have kept on the left side, on the single side, or we have separated them from the equation. All others are dynamic heads, are flow characteristics. Z is not a flow characteristic. It is basically a channel characteristic. So we can simply call it as delta Z. Keep it in mind, delta Z. And at this point, if the depth is Y1 or pressure head Y1, at this point it is Y2, it means that it will be Y1 plus delta Y1. It means that at section 2 head, our pressure head becomes Y2, which is equal to Y1 plus variation in head at point 1. It means that if it is 8 at this section, it will be 9 or something at this section. It means that it is 8 plus 1. Mean there is some part of Y which is added at section 2 in the original head of first point. And the same way, V2 will be equal to V1 square over 2G plus some part of V1 square over 2G. So these both are characteristics of dynamicity or kinematic flow. So if we want to write this equation again, so y2 will be equal to y1 plus dy1 minus y1, this minus y1, plus v2 square will be equal to v1 square over 2g plus differential of v1 square over 2g minus v1 square over 2g, this one as it is, plus hf. So this v1 square over 2g will be there, cancel this y1 with this one, and now the remaining equation will be delta z equal to dy1 plus dv1 square over 2g plus hf. So if we write the equation as delta z equal to dy1 plus differential of v1 square over 2g plus hf. So now we want to solve this simple equation. So let us say this is equation 2. If we draw a simple triangle including the bottom of the channel, this triangle, this one, with the parameters, this is the bed level, this is the horizontal line, and this is vertical line. We have called this as delta z, this length between section 1 and section 2 as dx, and this is the slope of the bed. This the slope of any line is basically equal to tan theta 1. So what is tan theta? This is equal to perpendicular over base. So what is perpendicular here? In front of theta is perpendicular, it is delta z over dx. So tan theta 1 here is s naught. So we can simply say that s naught is equal to delta z over dx. So what is delta z here? That is s naught dx. So we have got the value of delta z, which is equal to s naught dx. Because we want to ignore change in elevation head, we just want to add some channel parameters in it. Plus, we will just miss HF to find its value from the upper triangle. So now we will consider this triangle, upper triangle, this one with the slope SE and this line HF. So again, we will draw a triangle with a different scenario. This one. This is HF, head loss, between section 1 and 2. This is the line with the slope of SE because this is energy line. And this is again the distance between section 1 and section 2 as dx. Now again apply the tan theta 2 here. We can say this is theta 2. So tan theta 2 will be equal to the slope of the line, this energy line. So it is equal to SE. This is equal to perpendicular. In front of theta, we have a perpendicular, that is HF over dx. So SE is equal to HF over dx. What will be HF? HF will be equal to SE into dx. So just we will put the value of SE into dx in place of HF. Now shift the dx values on the one side. S naught dx minus SE dx equals dy1 plus differential of v1 square over 2g. Just take common dx from here. It will become S naught minus SE when dx is taken as common, dy1 plus differential of v1 square over 2g. Now we can divide by dx on both sides. To simplify the left hand side, this is simplified. So this is S naught minus SE is equal to dy1 by dx plus d by dx into v1 square over 2g. Now we want to take this because we are going to derive a differential relationship to determine the change in the elevation with respect to distance, as we talked in the introduction that there is a gradual change in water surface elevation. It means that we want to determine dy with respect to length of the channel, that is dx. So as we have to derive dy by dx, mean this thing is not complying with this term. So we have to convert this by a simple mathematical formula, that we will multiply this second term with dy1 and divide by also dy1. So what will this come? S naught minus Se equal to dy1 by dx plus, we can simply write it as dy1 over dx here, dy1 over dx into d by dy1, this d by dy1. This and this are mixed together, written over here, dy1 over dx into d over dy1 with respect to of v1 square over 2g. So what will happen here? We will just take dy1 over dx common from these two terms. Here we have taken this whole, so there will be only 1, plus it is also taken common from this term, so it will be d over dy1 into v1 square over 2g. If you want to ignore this subscript of 1, you can ignore, there is no problem. So if we simplify this equation again, dy by dx, I am not writing 1 or somewhat like this. So what will be the answer of this part? dy1 by dx or dy by dx. This will be divided on this side. So it will be s naught minus se divided by 1 plus d over dy into v square over 2g. S naught is the bed slope, Se is the energy line slope. So the problem is this point, this section. So now we will solve for this section. Simply, the, our term which is creating problem is d over dy into v square over 2g. So from the equation of continuity, we know that q is equal to av. We want to bring y in this equation to differentiate it with respect to y, because there is no y, so all constant term, it will become 0. So we want to induce y in this one by using the equation of continuity. So simply, if we want to know the value of v from this, so q by a, what is a in a rectangular channel? That is q to b into y. Because we have v square here, we'll simply take square on both sides. It will be square y square. So just put the value of v square in this equation. It will become like q square over b and y are in denominator. So it will be written with 2g, 2g b square into y square. Q is constant, G is constant, width of the channel or B is constant. So we'll write them as they are, 2GB square, and we will take the derivative of y raised to power minus 2, because in denominator it is y square plus 2, but when it will be taken to the upper side or in numerator, it will become as minus 2. So the rule of derivative is, whenever we take the derivative of any variable with respect to its own differential, it becomes, we take power in the start, n will come in start x, and n minus 1 mean power is reduced by 1. So in the same scenario we will do here, q square divided by 2g b square into minus 2 will become in start, and y will become minus 3. So if we again simplify this part, that this part will be equal to, after solving, it will be minus 2q square over 2g b square and y cube. This y was shifted to upper side just to take the derivative. When derivative is taken, we will again shift it to the denominator. It's y cube minus 3, and now it's y cube. 2 will be cancelled with the 2. It will be minus q square over g b square y square into y. I'm just making parts of this y cube. It will be y square and y, it's automatically as y. Now we know that v is equal to q by a, and we here as q square over b square over a square. y square, it means that minus q square, see here, q square over b square y square is equal to v square. Q square over b square y square, this term is equal to v square. We simply put the value v square here and we will write gy. As Froude number is given by v over gy square root, and if we take the square of Froude number, we'll have to take the square on the other side as well. Fr is equal to v square over gy because square root will be cancelled by square. So this term is basically equal to the Froude number. So here we can see this term v square over gy. So it will be equal to minus into Fr square, because this term v square over gy is equal to, by taking the square, it becomes Fr square minus Fr square. So simply we can say that after simplification, in this section, for in replacement of this section, we can simply write minus Fr square here in this equation, here at this part. So we can simply say that dy by dx is equal to S naught minus SE over 1 plus, and in place of that section, we will write FR square. If we again are further simplify this, this will be 1 minus FR square. So this is basically the equation or differential equation for the determination of water surface elevation for a gradually varied flow. So finally, it becomes to be dy by dx equal to S naught minus Se over 1 minus Fr square. So Fr is basically at section 1, mean Froude number at section 1. And we have to put the value of S naught Se, and then we will get a relationship of dy by dx, and we will be able to determine the relationship or profile, you can say the profile or water surface level of the water with respect to at different location. You can say at 1 meter, at 2 meter, at 3 meter, 4 meter, 5 meter, you will be able to derive a water surface profile like this one from the bed. So this will be known as the water surface profile. This equation is known as the differential equation of depth or water depth with respect to channel length of for gradually varied flow. So this is the final derivation of differential equation for gradually varied flow. In next lecture, I will discuss a numerical problem relevant to this, because in this section we have five types of profiles: mild, steep, horizontal, critical, and adverse slope profiles. So we'll discuss in the next lecture, and then we will discuss the numerical problem. So take care. Thank you very much. See you in the next video. Allah Hafiz.